Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive analysis of electrolytic capacitor failures, particularly focusing on the scenarios commonly encountered in older electronics, like those you might find in a Porsche 944 or similar vintage car. We'll cover the failure modes, causes, symptoms, testing methods, and even touch upon a practical example with code, using Python for data analysis. Understanding electrolytic capacitors. Electrolytic capacitors, particularly aluminum electrolytics, are polarized capacitors that utilize an electrolyte as one of their electrodes to achieve high capacitance values within a relatively small physical volume. They are widely used for power supply filtering, smoothing, and decoupling due to their cost-effectiveness and energy storage capacity. Construction. An aluminum electrolytic capacitor consists of two aluminum foils. One foil is etched to increase its surface area. A thin layer of aluminum oxide, Al2O3, is formed on the etched anode foil through an electrochemical process. This aluminum oxide layer acts as the dielectric. The electrolyte is a liquid or paste that provides electrical contact between the oxide layer and the cathode foil. A paper spacer soaked in the electrolyte separates the two foils. The entire assembly is sealed in an aluminum can. Polarity. Electrolytic capacitors are polarized, meaning they must be connected with the correct polarity. Applying reverse voltage can quickly damage or destroy the capacitor. The negative lead is usually marked on the capacitor body. ESR, equivalent series resistance. A critical parameter. ESR is the internal resistance of the capacitor. In an ideal capacitor, ESR would be 0. In reality, ESR arises from the resistance of the electrolyte, the leads, and the connection to the capacitor plates. Higher ESR leads to increased power dissipation, heat, reduced performance, and can contribute to failure. ESR increases with age and temperature. ESL, equivalent series inductance. Another parasitic component. ESL is the internal inductance of the capacitor. While usually less critical than ESR, it can become significant at higher frequencies. Capacitance. The measured capacitance value, typically expressed in microfarads, F. 2. Common failure modes in electrolytic capacitors. Electrolytic capacitors are known to degrade over time, especially when subjected to heat, high ripple current, and slash or voltage stress. Here are the most common failure modes. 1. Drying out / electrolyte loss. Description. The electrolyte gradually dries out or leaks over time. This is especially common in older capacitors, particularly those operating at elevated temperatures. Cause. Evaporation, diffusion through seals, chemical reactions within the electrolyte. Heat accelerates this process. Poor sealing. Symptoms. Reduced capacitance, increased ESR, increased leakage current. In severe cases, the capacitor can become completely open circuit, no capacitance. Bulging or rupture of the capacitor case can occur as internal pressure builds up due to gas formation. Impact. In power supplies, this can lead to increased ripple, voltage instability, and eventually, complete failure of the power supply. In signal circuits, it can cause signal distortion or complete signal loss. 2. Increased ESR. Description. The ESR of the capacitor increases significantly. Cause. Drying out of the electrolyte, corrosion of internal connections, degradation of the aluminum oxide dielectric layer. Symptoms. Overheating of the capacitor, reduced performance in filtering or decoupling applications, increased ripple voltage, voltage drops, and potential circuit malfunction. Impact similar to electrolyte loss, increased ESR can cause power supply instability, signal distortion, and general circuit malfunction. 3. Reduced capacitance description the capacitance value decreases below its specified tolerance. Cause drying out of the electrolyte, degradation of the dielectric layer. Symptoms similar to electrolyte loss, reduced filtering effectiveness, voltage instability, and potentially circuit malfunction. Impact reduced capacitance will affect the capacitor's ability to store charge and filter noise effectively. 4. Increased leakage current description the leakage current, DC current flowing through the capacitor when a DC voltage is applied, increases significantly. Cause degradation of the dielectric layer, contamination within the capacitor. Symptoms the capacitor may become warm or hot, especially at higher voltages. Increased power consumption, and potential damage to other components due to the increased current flow. Can cause voltage regulation problems. Impact can overload power supplies and potentially damage sensitive components connected to the capacitor. 5. Short circuit description a direct short circuit develops within the capacitor. Cause catastrophic failure of the dielectric layer, often due to overvoltage, reverse voltage, or severe overheating. Physical damage. Symptoms complete circuit failure, blown fuses, smoke, and potential fire hazard. Impact can cause significant damage to the entire circuit. 6. Open circuit description the capacitor becomes an open circuit, no connection. Cause severed internal connections, due to corrosion or mechanical stress, complete drying out of the electrolyte. Symptoms the capacitor effectively disappears from the circuit. Complete loss of functionality in the affected circuit. Impact the circuit will no longer operate as intended. 7. Bulging/rupture description the capacitor case bulges or ruptures, often accompanied by electrolyte leakage. Cause excessive internal pressure due to gas generation from electrolyte decomposition, often caused by overheating, overvoltage, or reverse voltage. Symptoms visually obvious damage, electrolyte leakage, a strong odor. Impact complete failure of the capacitor and potential damage to surrounding components from the leaked electrolyte, which can be corrosive. 3. Identifying failed electrolytic capacitors, symptoms and testing. Identifying faulty electrolytic capacitors requires a combination of visual inspection and electrical testing. 1. Visual inspection bulging look for bulging or swelling of the capacitor case, especially at the top or bottom. Leakage check for electrolyte leakage around the base of the capacitor or on the surrounding PCB. Electrolyte residue can be sticky or corrosive. Corrosion examine the leads of the capacitor and the surrounding PCB for signs of corrosion. Discoloration/burning look for discoloration or signs of burning on the capacitor body or surrounding components. 2. Electrical testing multimeter, basic check. Resistance measurement, discharged capacitor after discharging the capacitor, important, measure the resistance across its terminals. A good capacitor will initially show low resistance, which will then increase as the capacitor charges. A shorted capacitor will show very low resistance, close to 0 ohms. An open capacitor will show very high resistance, close to infinite ohms. Important asterisk: this is a very basic test and may not detect subtle degradation, such as increased ESR. Asterisk diode test, in circuit, very carefully some multimeters have a diode test function. You can use this to check for a shorted capacitor in circuit, but you must be extremely careful to avoid applying a voltage that could damage other components. If you see a diode reading, low voltage drop, across the capacitor, it's likely shorted. Always disconnect power before testing. This method is generally not recommended for in-circuit testing unless you're very experienced. Asterisk capacitance meter, accurate measurement. Asterisk a capacitance meter, LCR meter, provides a direct reading of the capacitor's capacitance value. Compare the measured value to the capacitor's rated capacitance and tolerance, usually printed on the capacitor body. A significant deviation from the rated value indicates a problem. Asterisk ESR meter, essential for accurate diagnosis. Asterisk an ESR meter is the most valuable tool for diagnosing electrolytic capacitor failures. It measures the equivalent series resistance, ESR, of the capacitor. Elevated ESR is a strong indicator of degradation, even if the capacitance value is still within acceptable limits. Asterisk typical ESR values. Asterisk ESR values vary depending on the capacitor's capacitance, voltage rating, and operating frequency. You'll need to consult datasheets or online resources to determine the expected ESR range for a given capacitor. However, as a general rule, ESR should be as low as possible, ideally, less than 1 ohm for most electrolytic capacitors. A reading of several ohms or higher is a strong indication of failure. Asterisk oscilloscope, ripple measurement. Asterisk an oscilloscope can be used to measure the ripple voltage across a capacitor in a live circuit. Excessive ripple voltage indicates that the capacitor is not filtering effectively, which can be caused by reduced capacitance or increased ESR. Asterisk procedure. Asterisk connect the oscilloscope probe across the capacitor, observing polarity. Set the oscilloscope to AC coupling and adjust the vertical scale to display the ripple voltage. Compare the measured ripple voltage to the expected value. Consult the circuit diagram or data sheet. 4. Failure analysis procedure for a 944, example scenario, fuel pump relay. Let's say your Porsche 944 is experiencing intermittent fuel pump operation, and you suspect the fuel pump relay. These relays often contain electrolytic capacitors for timing and filtering. Here's how you might approach the failure analysis. 1. Locate the relay. Find the fuel pump relay. Consult your 944's wiring diagram or service manual. 2. Visual inspection. Remove the relay and carefully inspect it for any signs of physical damage, such as bulging capacitors, burnt components, or corrosion. 3. Disassembly. If necessary, if the relay casing is accessible, carefully open it, usually involves prying it apart or removing screws. 4. Component identification. Identify the electrolytic capacitors on the relay circuit board. Note their capacitance, voltage rating, and any other markings. 5. Testing. ESR measurement. Use an ESR meter to measure the ESR of each electrolytic capacitor. Compare the measured values to the expected values. You may need to look up data sheets for the specific capacitors used. Capacitance measurement. Use a capacitance meter to measure the capacitance of each capacitor. Compare the measured values to the rated values. 6. Replacement. If any of the capacitors have significantly elevated ESR or reduced capacitance, replace them with new capacitors of the same or higher voltage rating and equivalent or lower ESR. Use high-quality, low ESR capacitors designed for switching power supplies or automotive applications. 7. Reassembly and testing * reassemble the relay and test its functionality in the car. V-code example, Python for ESR data analysis. Let's say you've collected ESR measurements from several capacitors during your failure analysis. You can use Python to analyze the data and identify outliers, potentially failed capacitors. Explanation of the code *. 1. Import libraries * imports NumPy for numerical calculations, Matplotlib for plotting, and Pandas for data frames. 2. Sample data * creates a list of capacitor IDs and their corresponding ESR values, replace this with your actual data. 3. Statistics * calculates the mean, standard deviation, and median of the ESR values. 4. Outlier detection, standard deviation method identifies outliers as ESR values that are more than 3 standard deviations away from the mean. Adjust the threshold as needed, a lower threshold will identify more outliers. 5. Outlier detection, IQR method identifies outliers as ESR values that are outside the interquartile range. 6. Visualization * creates a box plot, histogram, and scatter plot of the ESR data to visually identify outliers. The box plot is particularly useful for spotting values that are far outside the typical range. The scatter plot shows the ESR value for each capacitor. How to use the code *. 1. Install libraries * if you don't have them already, install the necessary Python libraries. 2. Replace sample data * replace the capacitor _IDs and ESR _values lists with your actual capacitor IDs and ESR measurements. 3. Run the code * execute the Python script. It will print the statistics, identify potential outliers, and display the plots. 6. Important considerations. Data sheets always consult the data sheets for the specific electrolytic capacitors you are using to determine the expected ESR, capacitance, and ripple current ratings. Temperature capacitor parameters, especially ESR, are temperature dependent. Measure ESR at a consistent temperature. Ripple current ensure that the replacement capacitors have a ripple current rating that is equal to or greater than the original capacitors. Excessive ripple current can lead to overheating and premature failure. Voltage rating use replacement capacitors with a voltage rating that is equal to or greater than the original capacitors. It is generally a good idea to use a higher voltage rating for improved reliability. Low ESR capacitors when replacing electrolytic capacitors, especially in power supplies or other critical circuits, use low ESR capacitors designed for switching power supplies or automotive applications. These capacitors offer improved performance and reliability. Polarity always double-check the polarity of electrolytic capacitors before installing them. Reversing the polarity can cause them to explode. Soldering use proper soldering techniques to avoid damaging the capacitors. Avoid overheating them during soldering. Safety always discharge capacitors before handling them. Electrolytic capacitors can store a significant amount of energy, even after the circuit is powered off. 7. Conclusion. Failure analysis of electrolytic capacitors is a critical skill for anyone working with older electronics. By understanding the common failure modes, learning how to test capacitors effectively, and using data analysis techniques, you can troubleshoot and repair circuits with greater confidence. Remember that proper replacement with high-quality components is essential for ensuring the long-term reliability of your repairs. Good luck with your 944.